Yeah, I guess. So there are actually a few topics that I want to cover. So there's this CHY formulas for Yang-Mills, gravity, and a few other theories. And then how do we see some properties that not manifest from old approach from such formulas, including relations among them and double copy and so on. So probably I'll do that first. Because I stopped at the bi-adjoint phi cube. From there, we could go to the geometry picture, but I think we can do that tomorrow. So yeah, so this part of the talk is mainly, I mean, let's write it down. The general thing I hope I convince you is that we can always write this thing as a localized integral with delta function imposed in the scattering equation. So by this I really mean dn sigma over SL2 and this product of scattering equation in the delta function of some integrand. And for convenience, let me write it in two parts. So as this is suggesting, I mean, it doesn't have to be that way, but in fact, in all the things I'm gonna, in all the theories I'm gonna tell you, they always look like that. That the integrand splits into two half integrands, and each has this property of having weight 2 under the SL2 transformation, as I explained. So a prototype of them is this formula for phi cube. So for phi cube, by adjoint phi cube, you have an integral. You have this I left, I right, both equal to color just Park-Taylor factors. That gives you the by adjoint scalar amplitude. Yes.
Do you know any series where it doesn't split?
There are. For example, from here, if you, I mean, this is really, say un cross un tilde. You say you want to get the single phi cube amplitude. Then it turns out it doesn't factorize anymore. So from here, you know there's this formula for just m alpha alpha, or just even, yeah, m alpha alpha is given by Park-Taylor alpha squared. This describes you the Catalan number planar cubic graphs, the sum of the Catalan number planar cubic graphs. As 4-point case, it's just as I wrote earlier, this 1, 2, 3, 4 guy with itself gives you 1 over s plus 1 over t at 5 point. Right? It's just the planar ones. You have 5 of them. I emphasize this again because we'll come back to this. This actually corresponds to vertices of some polytope. In general, you have Catalan number of such cubic graphs. But say you want to get this ordering is because you have this flavor group, and you did the decomposition. In particular, is only the diagonal piece of that. But say now you say I just want the amplitude for normal phi cube amplitude. But that's very simple. You just take the sum over all the alphas, right? Of all non-trivial, I mean, all the n-1 factorial orderings with some normalization, some number here. That gives you the phi cube, single scalar phi cube amplitude. That doesn't look like any factorized I left, I right thing. In fact, there's another example. If you want to get phi to the 4th amplitude, tree amplitude out of this thing is also not factorized. But I would say the thing that's naturally, the thing that I will focus on always have this split. And this is actually a game that we can play that as we go, we'll learn more building blocks. That's how this serves as some natural half integrand. And by just mixing them, you know, by just putting different building blocks together, we naturally get amplitudes of some theories. What are the scope of these theories that can be naturally described by CHY? We don't know. As I said, you can turn any amplitude into a formula. It doesn't mean it's natural. So far, what we get seems to have something to do with string theory. You know, you get Yang-Mills, you get GR, but you also get like the DBI and type of thing that I'll come to in a second. Okay, so let's do Yang-Mills first. So very naturally, now you only have one copy of the flavor. So the conjecture is that you start with this C, color just the Park-Taylor, and then you want something for the right integrand. Now it can depend on sigma k, but crucially, it also should depend on polarizations, right? I mean, now you're not describing scalars. You want something. And from some property I'm going to tell you later, you can prove that if your Yang-Mills amplitude, so here, of course, you can deduce the formula for this is completely equivalent for a given ordering. Now you just do the color decomposition, you get Park-Taylor alpha here, time the same I write, right? So there are some properties that this partial amplitude satisfy, like Kleist-Koeff relation and BCG relation. I'm sure you know that very well. From there, you can actually turn into a statement about this guy. So this guy has to be permutation invariant. In other words, all the information about color ordering and so on is encoded in this factor. Okay? So we are looking for some permutation invariant half integrand that depends on polarization and the momenta. Yes?
Is there some significance to the fact that when you impose all those conditions, the number of independent color orderings is the same as the number of solutions to the scattering equation?
We'll come to that. Actually, the number of independent partial amplitudes will be n-3 factorial. Yes, they are related. I'll explain. Yeah, when we come to the relations among amplitude part. So I'm not going to motivate you how to guess that thing. That's how we originally did. You know, you try to come up with something that satisfies some very simple property. First, as I said, it should be a permutation invariant. What is the property of this I right? It should be a permutation invariant half integrand, meaning it should have same transformation property as a Park-Taylor, has weight 2. Second of all, it needs to be multilinear in all the polarization, right? This is very simple. So in all the polarization vectors, that's what you expect. And in particular, if you're doing Yang-Mills, you're not doing some higher dimensional operator theories with higher dimensional operators. It can have at most epsilon dot k to the n-2 power. So this is like power counting from Feynman diagram, you already know. But most crucially, well, there are two very crucial non-trivial properties that I want this guy to satisfy. First is it should be gauge invariant. So this is in sharp contrast with Feynman diagrams where individual terms are not gauge invariant. But here, since we're writing the whole thing as a summing over solutions of some I left, I right divided by the Jacobian I talked about, we really want the thing to be gauge invariant on every solution. Okay, so on the support of the scattering equations, we really want this thing to be gauge invariant. Meaning, if you replace an epsilon I mu by ki mu, you should get 0. Just linearize. And last, you wanted to satisfy Soft theorem, Weinberg Soft theorem. Okay, so basically, what we construct, I mean, from that's actually the way we want to construct this thing is by trying with ansatz and using this constraint. But the answer turns out to be extremely simple. And now we also understand, I mean, later we also understood better why there's such an object, because it's closely related to the actual open string correlator. So let me just write down the answer. The answer turns out to be the reduced Pfaffian. Well, Pfaffian is just the square root of a determinant for an anti-symmetric matrix of this 2n by 2n anti-symmetric matrix that takes this block form. So it has this 4 blocks, each n by n matrix, where this take it to be minus C transpose, make it anti-symmetric. So this 2 has to be diagonal thing has to be anti-symmetric by itself. And they are very simple things. So the A matrix is just things we already see from scattering equations. If for the off-diagonal piece and diagonal, of course, you should get 0 because it needs to be anti-symmetric. And B is the direct analog of that, where you have contractional polarizations, polarization vectors with theory diagonal. The C part is, you can guess now that at least for the off diagonal, it should be something like that, right? So epsilon dot k. Now the diagonal thing is interesting. Let me leave it. I'll tell you later. So the basic idea is that actually if you really try the full-fledged string correlator of n vertex operator of gluons, you get something that's related to this matrix but more complicated. You have some alpha prime dependent inhomogeneous piece in alpha prime. But now if you use scattering equation, you can show that you can eliminate them actually. Okay, so that's a very important thing that later we realize we don't have to guess and do this. But now let's just finish this. How do I see that the thing I want to compute is basically the Pfaffian of this matrix that satisfies this property. Let's just see this quickly. Okay, so actually it's the reduced Pfaffian, because just like this Jacobian, this determinant prime phi object we talked about. Remember, this guy has this derivative matrix of scattering equation has 3 null vectors, right? So you need to delete before you compute its determinant. Here it's similar. This matrix, if you now check, it has 2 null vectors. I'll leave it as an exercise. So these are 2 n vectors. It has 2 such null vectors. Well, I guess if you need to check, I need to tell you what C looks like. Let me just tell you. So it looks like epsilon A dot KC over sigma AC, C different from A, if A is same as B. I mean, it's very, you expect this, right, as a sum of the off-diagonal things. If you look at here, it's actually also same structure for A. But because of scattering equation, this gives you 0. Okay? This is the scattering equation for A, for particle A. So here you are just replacing the Ka by epsilon A in exactly the same manner. So if you plug this in, you see the matrix has these 2 null vectors. Remember, it's a 2n vector that, so the second part is all 0. So I'm not summing over different I'm not summing over entries with different epsilons. That you shouldn't do. I'm just summing over entries with different k's. So the first the n by n matrix is column and rows are labeled by the k1 through km. Because of these 2 null vectors, your Pfaffian of this matrix is actually defined as a reduced Pfaffian, just like there's a reduced determinant, which is you delete these 2 columns and rows. Remember, it's only deleting from the first n columns and rows. So I and j are referring to the first n guys, and there's a Jacobian that you pick up, sigma ij. Okay, sorry, the Pfaffian of this 2n minus 2 by 2n minus 2 matrix after deletion. Okay, so you can show this thing is permutation invariant. It's independent of the thing you delete. Now comes the question: why is this a good object? As I said, it's independent of ij, so it's manifestly permutation invariant because of the construction, right? Now it's also a half integrand. That's crucial. You don't take the determinant of this matrix. It's already a 2n by 2n matrix. If you take a determinant, you get too high weight in the sigmas. And obviously, so this rows are labeled by k1 through kn. These rows are labeled by epsilon 1 through epsilon n. They are multilinear in all the epsilons, where you deleted 2k. So the mass dimension is correct. It has n minus 2 power of k, where it has n epsilon, right, when you expand your Pfaffian. So really the non-trivial thing you need to check is this 2. Okay, the soft theorem I'll probably leave it for later, but let's check the gauging invariance. I think it's pretty important that it's the only object I know that you can construct that make gauging invariance manifest at individual piece. It's really for every solution the gauging invariance now should be completely manifest. So for that purpose, we just need to look at the first row and also the n plus 1 row of the matrix. Let's just write it down explicitly. So you have the A part that start with a 0, and now this is the first row is labeled by k1. And also the C part, now you have, let me see, is it also K1? Sorry, the first one is C11 minus C11 actually. I leave it like that. And then it's K1 by epsilon 2 over sigma 1, 2. and then all the way to k1 dot epsilon n by sigma 1 n, right? And now you have the for other things until you reach half of that matrix here. Now I write the next one. This row is labeled by k1. This row is labeled by epsilon 1. Here again you see c1 1. Now I have epsilon 1 dot k2 sigma 1 2 all the way to epsilon 1 dot kn sigma 1 n. So here's the other line. On this side you start to see the b part. So 0 epsilon 1 dot epsilon 2 all the way to epsilon 1 dot epsilon n, right? So why I'm looking at these two particular rows, because they are the only place you see, well, actually this one and this entry are the only place you see epsilon 1, okay? Now I'm going to do the replacement that I'm going to replace, in my matrix, I'm going to replace, say, epsilon 1 by k1, okay? I'm doing a shift of epsilon 1 goes to epsilon 1 plus any multiple of k1, but for simplicity, I can just replace it. So you see this one becomes k1, k1. So immediately see that these two rows become identical, except you need to check this guy, which is just before it was epsilon 1 dot ki sigma 1I sum over I, right? From 2 to n. Now I replace this epsilon 1 by k1, it's scattering equation. So really on every solution of scattering equation, C11 crucially it goes to 0 when I replace epsilon 1 by k1. Okay, so this is how you actually come up with this idea of writing down a diagonal of C in this way. So now this matrix, you replace it by 0. So this matrix develops even more null vectors than the original two. So now if you compute its reduced far field, you get 0. So this is how you guarantee gauge invariance in this very nice way. So immediately you can recycle it for gravity now. So you really don't need to think. Here's the nice thing about it. So all the properties you want, I'll show you soft theorem in the end if I have time. So actually, yeah, Weinberg soft theorem also come very nicely as consequence of the formula. Actually, even including like subleading corrections that people discuss in recent years. So, but let's check the first three properties now for gravity that you can easily write down another formula. Let me write it. Let me not keep this one, but write down the one for gravity. Now you don't need color. Okay, this is for color. So for Yang-Mills, as I just said, this is a reduced far field of something that let me emphasize it's a function of epsilon, okay, of the polarizations. Now for gravity, you really don't need a color, but you can have both your I left and your I right can look like a far field with epsilon and epsilon tilde. Now your polarization tensor, this guy, can be just made of epsilon mu and epsilon tilde nu, okay? So why does this make sense? Because it has all the same property as before. Now it's now it's like a determinant if epsilon is the same as epsilon tilde. So it's multilinear in this guy, as the same mass dimension as Einstein gravity. And now its gauge invariant is the linearized diffeomorphism invariance that you can again trivially check because of the far field, right? You can do actually the shift in both on either side to see that. And in particular, if it's really the symmetric traceless part that you're concerned with, then you can set epsilon and epsilon tilde to be the same. So this guy is literally determinant, reduce the determinant of an object, okay, of this matrix. The left and right become the same. So this is really in very parallel. Like the gravity CHY formula is for closed string, and like type 2 kind of you put left and right to be the same thing. And this is more like a heterotic string that on the left you describe color and right you describe the polarizations. Okay, so this is now you need to prove this. The easiest way, say you can prove it using say BCFW, like what Goddard and Dolan did. But you could also expand these things in Park-Taylor and just compute. You can just compute the answer and then check the answer is correct. So actually that's a practical way of getting some closed formula if you want, or getting BCG numerator in some way that later I'll describe. It's literally by expanding such things. I mean the Park-Taylor is already in Park-Taylor basis, but these guys, although it requires some work, that it doesn't, naively when you expand the matrix, you see things that doesn't look like Park-Taylor. But on the support of scattering equation, you always can simplify them into things like Park-Taylor, meaning there's no double pole and so on in sigma. Once you are there, you're done. You just use the formula I erased for m alpha beta to evaluate the final answer. So that's actually how you do practical computation if you want to use this thing. You never really solve scattering equations, okay? And the advantage of this representation as an integral formula or summing over solution is that it's manifestly gauge invariant and so on. The disadvantage is not obvious from here that they can be expanded in Park-Taylor. You have to work. But once you are there, you lost gauge invariance, but you recover something that's completely just made of the m alpha beta. Okay. So this is the first two theories I wanna tell you, and now you can really just play with more integrand. So here you already see that we have half integrand. Here you already see that we have two half integrand that we like. One is a Park-Taylor, the color just one, and the other is this Pfaffian. And by putting them in three different combinations, we recover phi cube, Young-Mills, and gravity. Now you can do more, right? You can get some. So now I'm trying to describe you some operations that you can apply to this formula, just very briefly. I won't go through all of them. That you can get new formulas out of it. So amplitudes, formulas for amplitudes in some new theories. Okay. So of course there are some very trivial ones you can think of. Just do dimension reduction or compactification just to the massless part. If you do that, you get theories like Young-Mills coupled to scalar, the dimension reduction of Young-Mills theory to lower dimension, or graviton coupled to photon, Einstein-Maxwell theory. You get the amplitudes for them for free, right? This is just an advantage of the fact that you're working in D dimension. So you can do that because they all introduce you some nice ingredient that we're going to play with. So let me show it for you actually. So the thing I want to do is this reduction, that if I have a d-dimensional massless momentum, I reduce it to lower dimension by this. So this is my d-dimensional one, and this is my small d, and here I have the internal space. I just choose it to be 0. That this is massless. Now I can do the same for my polarization, but now I have two choices. So if I start with my Young-Mills case, I start with a gluon. When I dimension reduce, I either still have a gluon with this 0 I denote the set of gluons after reduction by G. Okay, or I could get something like that. I have the external part is 0, and internal part is some unit vectors in this internal space. So this is for the particles that were reduced to scalars. I denote the set of them by S. Okay? So I'm just saying this trivial operation of plugging in such K and epsilon into your formula here gives you the formula for the Young-Mills, for the dimension reduction of your Young-Mills theory, which is, if you ask me I mean, it's of course guaranteed by the validity of this formula, but it's still kind of interesting. After the reduction, you get some formula. On the other side, you get some different Lagrangian, right? The Lagrangian for the scalar coupled to Young-Mills. And they actually play a role in the thing I'm going to tell you now. So the Pfaffian matrix just look like this now. So the A part is not changed, right? The A part just become the A part in lower dimension. But the C part and B part becomes more interesting. So if I use this to denote the gluon set, and this is the scalar set. It doesn't have to go from 1 through n now. That this is just my usual C matrix for the gluons. This is 0, right? Because this dot that is 0, epsilon dot k. And similarly here, I have minus CG transpose and 0. Now the B part is similar. I have a B for the gluons, and now I have 0, 0 here, because there are inner product is 0, contraction. And here I find a new matrix for the scalars that's defined as xab equals 0 for the diagonal piece as before, but also it's like EA dot EB over sigma AB for the off diagonal piece, where I can choose to normalize the EA of EB to be delta of the internal index. So this is my flavor group now. Now my scalars are further flavor under flavor group OM. Okay? So just take the phi field of this matrix now, which reduced to, so the phi field of the reduced phi field of the original thing becomes phi field prime of A, phi field prime of this small this matrix. Okay, this matrix is the original matrix that you choose only the gluon part for the epsilons. Let me denote it like that. And then phi field of this X scalar part of the, this is purely just some 1 over sigma AB thing that encode the flavor structure of your scalar. So this, in this way, you get some formula for Yang-Mills coupled to scalar, or if you do it this way to one of the side, you get the formula for Einstein-Maxwell theory, right? I mean, this is all trivial, but let's focus on actually a very particularly clean case where I'm reducing to pure scalars. So I wanna see what's the formula for the scalar coupled to gluon in lower dimension, but I want the external legs to all be scalars. Okay? This is the scalars are coupled through gluons, but they also have a phi to the 4 type of interaction from the reduction, right? So now the formula is particularly simple. So let me write down a formula for you for the Yang-Mills scalar case where I have n scalars. It's just the Park-Taylor part is not changed. And now you have a phi field prime of A, because this shrinking to just A, right? And then phi field of the whole matrix X. Now it's all n by n matrix now, right? So you see some new building block. That's fun. So we although they are just some special case of this dimension reduction, but we recognize 2 new things. One is just the phi field of this A matrix. The other is this, okay? So they are actually not even half integrand, they are quarter integrand. So each of them behave like weight 1 object, right? They made up to a half integrand. So now you can play with them. Now you can say, let's build formulas using these building blocks, okay? To see what we get. So that's why I spend some time on this trivial reduction. It's kind of cool. I mean, if you ask me why this formula, I mean, apart from the higher dimensional thing, why this formula describe you the way that scalar, I mean, coupled to gluon and so on, it's not easy to answer. But now we can even use them to cook up some new formula, just like what we did before, where we only have the Park-Taylor and the phi field prime side, right? Now we can play with them. So, I mean, basically what you can write down is you can take phi field prime A to some power, phi field X to some power, and then also say the Park-Taylor or the C to some power, right? I mean, you can play this game where we're just listing scalar theories now without the psi. So there's something you cannot do, which is well, let me first list them. So if you do have this guy, the first formula we have already there. This is all first power that you get. Pure scalar amplitude in the dimension reduction from Yang-Mills, right? Now you can have a formula where you take this guy to square. Now it's a quarter integrand, so if you square it, you get a half integrand, right? Forget about this guy. What is there a meaning to this formula? I mean, you're all doing CHY integral. Or you could take no Park-Taylor, starting to distribute the, I mean, here you could also say, let's take a formula like that. Phi field X squared. I'll tell you this is not sensible in a second. But then you could forget about Park-Taylor. Let's just take this thing. So you could say, let's do phi field prime A, phi field X, both squared, right? We can do that, right? And then we can do phi field prime A cube, phi field X. We can do phi field prime A to the 4th. We can also do phi field X to the 4th. This is really stupid, just to make up the weight, okay? So out of here, you can immediately recognize, actually, you cannot take this thing or this thing. I mean, I probably forgot also the Pfaffian x cube. Anyway, you want to keep the Pfaffian x. The reason you're throwing out this such half integrand is because they give you double pole. Okay, very easily you can see they give you double pole. But you can take higher power in Pfaffian prime A because they have numerator sitting there that's SAB, like Ka.Kb. So that kills you those double pole you produce. So just play this mathematical game. You already see that the CHY integrand of this kind of things are reasonable, which only have simple pole, but those others are not reasonable. By the way, these are all theories that only have even multiplicity structure, right? So because if you have odd number of particles, this kind of matrix, the Pfaffian vanishes. You cannot write down this. So what are these theories? Now it's a very interesting question. What are these theories? I just said this is the pure scalar part of the Yang-Mills scalar, which come from dimension reduction of Yang-Mills. And this is actually the nonlinear sigma model. So the low energy Lagrangian that you use to describe massless pions. So you can see why that should be a candidate, because this needs to be a scalar theory that has some derivative coupling because of this A matrix structure. It has some Mendel sum in the numerator, but also should have color. So it's really like UN nonlinear sigma model, for example. Okay. What is this? This is like the double copy of that. So it appears in some Einstein-Maxwell scalar theory, the pure scalar component of that. And this theory is less interesting, but this theory turns out to be very interesting. This theory is the Dirac-Born-Infeld, the pure scalar part. I mean, the thing people usually call DBI, but I mean, if general DBI is like Yang-Mills scalar, you can have photons and scalars coupled together. But if you only care about its pure scalar part, you get a consistent truncation, and it's given by this formula. It makes sense because, first of all, it doesn't have color, and then it has even higher derivative coupling. Okay, so this is describe you another effective field theory. This is what's the extreme. So this is even higher dimensional coupling. So let me give you like examples of these things at 4 point. So the nonlinear sigma model of amplitude, a nonlinear sigma model at this ordering is like S plus T, right? While the DBI 4 point is like S squared plus T squared plus U squared. And then now you have this theory. If you compute it, you can view this as an exercise. It's something like STU. Okay, it's even higher dimensional. So what is this theory? It's actually a special Galilean theory that it's not just so just like in these two cases, they are not just a random effective field theory for these particles, for pions. They are the one that has some special property. So same here. So all these theories has only one coupling. Okay, so this in general this Galilean theory is an effective field theory that at higher and higher order you have different couplings, but there's some property for the special one. There's a hidden symmetry for the special one that actually tells you all the higher point coupling are determined by the 4.1. So just like DBI and the nonlinear sigma model. So this is actually understood from the effective field theory point of view as some I think Yura and the collaborators, they call it exceptional EFT. Okay, so these are the 3 examples of the exceptional EFT, in the sense that they are determined by some very simple properties, which is actually enhanced, in general, enhanced at the 0. So if you take a soft limit of any of these scalars, this amplitude goes like order tau square, and order tau cube. That is not obvious at all from Feynman diagram. It's an enhanced cancellation when you sum over all Feynman diagrams. And CHY formula actually makes it completely manifest. You just count how many Pfaffian prime A you have, then you see the soft property. So in some sense, there's nothing to check now, because I mean the way we identify this theory with this building block is by really computing the amplitude and then read off the Lagrangian, and then we discover these theories. But after their paper, you just recognize, oh, there are only unique theory that has order tau, unique theory for order tau square and order tau cube at the 0. That's it. Those CHY formula manifestly have those enhanced soft limit, so they must be those theory. Okay? In fact, it's quite difficult to really prove it without this input because you can check factorization, but then you have contact term every order. So you really need to work hard to really prove it as you did for Young-Mills and gravity. So these theories are really the analog of Young-Mills and Einstein gravity in the effective field theory context, because though their things are fixed at that mass dimension uniquely by gauge invariance. Well, here it's fixed by this enhanced Adler zero. There's really an analogy between things. So, yes?
Can you go to more general EFCs?
Now you have to cook up new building blocks, and you have to. In general, if you want to add, if you want to deform the parameters like for higher dimensional couplings and higher point coupling and so on, it cannot be described as something so simple, right? It has the coupling has to enter now. So all these things are More questions? Yeah.
What about with the non-abelian DBI?
Yeah, it's a good question. So we don't know. So there's some in the connection with string theory, there are some attempts in writing down formula like that, but we still don't know. Yeah. By the way, since you mentioned this, I can recover the Born-Infeld formula from here, right? I just need to recognize that this is actually like that, and this part comes from the dimension reduction of my original Pfaffian prime psi. Okay? So if I write down this Pfaffian prime A square Pfaffian prime psi thing, that is describing me some derivative coupled photon theory that's known as the Born-Infeld theory. Here I think, it's not effective field theory of scalars, but rather of photons. So there's really this big web of theory that's connected to each other through some simplest case is dimension reduction, but in this more general case, you can argue there are some operation you can apply to it to connect, say, Young-Mills with nonlinear circle model or gravity with Born-Infeld and so on. That I will not describe here. Sorry? Yeah.
And how would the supersymmetry, if we want to have,
Yeah.
how does it show up?
Then you need to go to some particular dimension. Here is valid in any dimension, and it only applies to bosons. If you want to have supersymmetry, you need to go to, say, 4 dimension. You can naturally supersymmetrize the formula, or 10 dimension or 6 dimension. There are formulas for this supersymmetrized Young-Mills or DBI and so on. Yeah. So there's a second class of operation which I won't have time to describe here. That is essentially like adding non-abelian interactions to the formula you already have. For example, if you start with Young-Mills scalar, now you can try to add some non-abelian interaction among the scalars by minimally coupling it to the bi-adjoint phi cube I described. So now this kind of theory has at least 2 couplings, the Young-Mills coupling and the phi cube coupling. Or here, you can make it Einstein Young-Mills. By not only the Einstein-Maxwell only has the Newton, has the kappa, now you also add G Young-Mills by minimal coupling. There's a natural generalization of the formula, which I won't describe here, to describe such theories. So you really have a big web of things, and these are the and there are some other theories that are naturally described by CHY, which I will not go into details. For example, I can make one example. So if you say I want to describe gluons coupled to graviton, right? So it's really in between. So we know that the pure graviton amplitude looks like that from CHY point of view, and the pure gluon one look like this, right? So what's in between is you keep this guy not touched, and you find some object that interpolate the two. Say in the single, now your gluons doesn't have to be in a single trace. You can have multi-trace gluons with graviton propagate in between, right? So, but if you just do the single trace one, say you have some Park-Taylor, you have 1 through m, that's your gluons, and then m plus 1 through n is your graviton, you simply do this. So remarkably, it worked. Now you don't have the prime because you lost the null vector. So you really just take the part of the Pfaffian that has this polarization of these particles, and you take the Park-Taylor. This describes you the single trace minimal coupled gluons with gravitons. And now you can go to double trace. Anyway, there's a series of operations. So you might wonder, maybe, say, if you consider external gluons, only external gluons, you may wonder if this is your double trace amplitude with all two orderings. Unfortunately, it's similar to the far-field X kind of thing to some power that it has double poles. Okay, so it has double pole in this subcycle. So now you're forming some subcycle. But the fix is really simple. You just put a pole here. This turns out to describe you the double trace amplitudes in Einstein-Young Mills. And there's a generalization of it to all kinds of amplitudes obtained. So let me be, I mean, it's really, from this point of view, it's really mysterious why, I mean, there are some nice properties saying these amplitudes are unique in some sense, but it's really, we don't really know how to, what this operation mean at the Lagrangian level, right? So this is I think a interesting open question. As the question referring to, if you are now changed to some other general effective field theory for scalars, how do I change the CHY integrand to do that? We still don't know. Okay, so let me switch to the next part, which is the how to see the relations between amplitude. This is already telling you some relations. That's essentially the way we obtain, like by doing dimension reduction or generalization of it, and also by adding, by coupling different formulas together, by putting their interactions together. Okay, so the next there's some very interesting relations. This color kinematics duality and double copy, that's the next topic I want to talk about, which actually not only apply to Young-Mills gravity case, but also to these cases, because they turn into some mathematical statement about the formula itself. So I'm going to talk it in two steps. One is I want to describe just the on-shell relations, now as so there are this KK, Kleist-Coif, and BCJ relations for partial amplitude, for all the, say, for A Young-Mills of different orderings, right? And there's also the KLT relation. I'm sure you learn probably both lectures of string amplitude. And so this first appears as the double copy relation of closed string and open strings amplitudes. And taking its field theory limit, it's at tree level equivalent to the BCJ double copy when you have arranged color kinematics duality. And the second part I will go to the actually color kinematics duality and double copy. Okay, they are equivalent at tree level, but we see how both of them nicely turns into just some mathematical statement of this integrand. So first, the simplest thing. So actually, I could have motivated the whole discussion, the scattering equation from this point of view. How are amplitudes of Young-Mills and also other things? Let's take Young-Mills as a starting point. So how do amplitudes like that satisfy, why do they satisfy Kleist-Coif relation or BCG relation? I think that's a very interesting question to ask, because now you have that's the advantage of having a formula for it. Now you have a formula, you want to see what's going on, right? So the Kleist-Coif part turns out to be very simple. So I mean, that I leave as a, well, I guess I'll leave both as exercise for you now. So they are, let's come back here. They are actually properties about Park-Taylor half integrand. They have nothing to do with this part, because this is some permutation invariant thing. When you compute different color ordering, they are always stay the same. So the Kleist-Coif relation, or the U1, let me just do U1 decoupling relation, is simply this trivial identity, right? This identity for the Park-Taylors. So when you say the U1 decoupling here, you pick your particle 1 to be photon, it has to decouple from the amplitude. So you do the color decomposition, you see the A Young-Mills has to satisfy this relation. I'm sure you've seen it before. Now it turns into a statement in a CHY context that the Park-Taylor has to satisfy this relation, right? But this is trivial. You can really just verify it. This is some algebraic relation among the Park-Taylor factors defined like that. Okay. Now comes more interesting, the BCJ. Well, this is the fundamental BCJ can be seen trivially can be seen as a following, translating to this following identity. Here you put 0 times this Park-Taylor. I mean, this is just a translation of the fundamental BCJ. This is S12, right? As I said, I could have started motivating the scattering equation and everything from this point of view. So the last one is just S12 plus S13, S12 plus S13 plus all the way to S1n minus 1 times that Pactator. 2, 3 to n minus 1, 1, n. Sorry, how much time?
You got 15 minutes.
Oh, great. Okay. So yeah, this term is gone. So this is, say, one fundamental BCJ relation. Now translated, I mean, into the statement about Pactator. Why is that true? This is very, at first sight, is very mysterious because these are just sigmas. Now you have S, but they are true because of scattering equation. Actually, this is not even worth leaving as an exercise, but this I'll leave as an exercise to show that this formula, this left-hand side of this identity is actually proportional to this formula. So I from 2 to n S1i sigma I over sigma 1i. So in other words, all I need to show is this is 0. So actually the left-hand side is proportional to this times some Pactator with no 1. Okay? Times this Pactator. So this is literally just translated. And now this is, if you remember, I mean, after very trivial manipulation, my scattering equation 1. So it's really, you can turn the logic backwards, saying, if I learn from what Wheaton had that I want my formula to be described by some Pactator factor times some permutation invariant object, when will this amplitude satisfy BCJ? Then if and only if my punctures satisfy scattering equation. So this is another way of discovering scattering equation, and that's actually what Freddy found in his paper, but in the context of twistor string. So he found that in twistor string, those punctures satisfy relation like that, where you write S1i as 1i and 1i. So from there, he could just immediately uplift to our scattering equation in D dimension. So yeah, so actually, yeah, here is just particle 1, but if you want all BCG relation, you need all scattering equation. Okay? So I think this is kind of cute, and now immediately it applies to all formulas with a Pactator, like nonlinear second model. You don't have to say why. Yeah, I'm going to other things, but it immediately also say now you want to write down a formula for, say, the higher dimensional operator like f cube. If you want to have an amplitude with one insertion of f cube operator, you know from string theory, from bosonic string, that if you expand the monodromy relation, it satisfies BCJ. So you already know from the beginning it has to come as a Pactator times something permutation invariant. That is no longer true for general higher order corrections in string theory. They don't necessarily satisfy field theory BCJ relations. So for those, you need to do something else. So there's all this question of determining higher dimensional operator corrected connection to the string amplitude, which is very nice. So here you can already see that BCJ relations tells you how to reduce to n-3 factorial independent partial amplitude. Or in other words, if I forget about scattering equation, just algebraically, the space of Pactators, the space of rational function made of Pactators are n-2 factorial dimension, right? Dimensional. Now, if I consider the puncture satisfy scattering equation, I immediately see the space of those linear combination of Pactators n-3 factorial dimensional, which is the same as the number of solution. And now I will use this fact to derive KLT. So we'll see that KLT from this point of view is really about any formula that you have that looks like I left and I right, product of two half integrand, and you want to split it into so it's rather than product, take product of two things. You start with the target that you have, say some, if you say a theory is described by this, with I left and I right being half integrand, then you can discover KLT by splitting this formula. It's really by inserting a complete basis to discover KLT. And this uses crucially that your number of solution is the same as the dimension of that auxiliary space you're introducing. So I think this is really a very, very interesting, let me go through it quickly. So what do I mean by this formula? As I said, it's really summing over solution I from 1 to n-3 factorial of some bilinear thing that I write it in this way. So I call this I left divided by my determinant prime phi. I just make it symmetric. And I right determinant by my determinant prime phi, both evaluated, well, let me do it even more redundantly, that this thing evaluated as solution I, this thing evaluated as solution J times a matrix Dij that's actually diagonal. So this matrix Dij is defined as determinant prime phi evaluated at solution I chronicle delta ij. Okay? So this is just, I've done nothing. I've only just split the 1 over determinant, 1 over Jacobian into 2 pieces and put it back here. Okay? So this is in some sense, I mean, any CHY formula with these two guys is like a direct, like an inner product with this matrix in this solution space. Okay? Now I want to change bases. I want to go to an auxiliary space. I can do the following. So remember, this dimension of the solution space is M-3 factorial. So my auxiliary space has to be M-3 factorial. Let me introduce this some basis for that auxiliary space. It's also M-3 dimensional. So one set of bases L. This is a vector of dimension M-3 factorial. L depend on sigma, and the other one is R depend on sigma. Okay? I can introduce this. They don't have to be anything you know. They are just function of sigma that are independent under the scattering equation I just described. So you can choose any basis you want. Now I want to insert them there to rewrite it as some inner product in this auxiliary space now. Okay? So actually, you can prove this very trivial. You can prove this. The Dij I just wrote there is nothing but L. So this vector I use alpha and beta to label this auxiliary space thing. Okay. So far I haven't told you what are they. They can be orderings. They can be other things. So I use L alpha I to denote the alpha component, and my sigma I. Let me just write like that. Sigma is evaluated at solution I. So this is a n-3 factorial dimension matrix. Okay. And also I have right beta sigma evaluated at J. Now I put a transfer, the matrix transforming between the two is actually the inverse of a matrix that I call M. What is this M? M is defined as just the L alpha sigma I Dij R beta sigma J, right? So you can easily show this identity. This M alpha beta is defined by summing over Ij here. Okay? So all I'm doing is to introduce a change of basis matrix from this solution space to some auxiliary space. So there's this M, that's like the matrix in between. And now I express my Dij as L, M inverse, and R. I plug it in here. Okay? So once I plug it in here, it's very simple to see. Let me continue here. That I got some inner product in the auxiliary space now. So I really just get that I left over determinant prime phi thing times this L alpha sigma evaluated at I. Here also the whole thing evaluated at I, right? Yeah, let me just say the whole thing evaluated at I, and I need to sum over I. Okay, sum over I, and the other side I get I right divided by determinant prime phi, and also R beta evaluated at solution J, and I need to sum over J. Now I put in these two things. Now they depend on alpha and beta. They are in the auxiliary space, two vectors in the auxiliary space with this M inverse matrix of alpha beta, sum over alpha beta. Okay? I think it's probably I definitely lost you. So yeah. So let me put some brackets so pretend that you totally understand. So now this guy is after summing over solution, some auxiliary space vector alpha. This guy is some auxiliary space vector beta with this inner product that's defined here. Okay? But now notice all these three things, the M in the middle and these two guys, they are CHY formulas. So now you're done. So what is this? This is a CHY formula of your I left with this L of alpha, right? You do CHY integral because that's just the Jacobian sum over solution. This guy is the CHY integral of I right with your R of beta. And all I have shown is if I start with this formula, I can split the formula into two amplitudes whose half integrand are given by I left and some basis, I right and some basis that depends on indices in the auxiliary space with a matrix, the inverse of a matrix in between. And that matrix itself is defined by a CHY formula that's d mu n L alpha R beta. Okay, so this is the conclusion. I start with the formula, I split into two formulas with basis, where the matrix in between comes from the inverse of another amplitude. Okay, so now this I want to emphasize this is completely general. So you can do it for if you find any M-3 factorial basis L or R, you can do this. Now you're splitting your formula into some amplitudes. The problem is, do you know this as some nice amplitudes or not, right? And do this guy also look nice? So far, actually, it's an interesting question to find such nice basis. So far, the only thing nice we found for this L and R are the particular factors of ordering alpha and ordering beta evaluated at, yeah. So that gives you the KLT relation. That's the last thing I want to write here. So you really, if you use the particular factors as your basis, you split your formula into, so your I left, I right integral now becomes this I left with a particular alpha, I right with a particular beta, or CHY integral, with this M inverse, where M is something I told you before, M inverse alpha beta. M is this matrix of, that's why I emphasized a few times. This M matrix is quite important. It's just CHY integral of particular alpha and particular beta, the double partial amplitude in the bi-adjoint scalar case. It turns out that it's inverse. Notice it's in some basis. Okay, this guy is by itself is n factorial by n factorial matrices, but it has null space. So if you go to the basis, it's n-3 factorial. Now you can take its inverse, and this is nothing but the KLT kernel in some. Yeah, you can. Even here, even when you restrict yourself to particular alpha and beta, there's still huge redundancy. You can choose what n-3 factorial guys and what n-3 factorial orderings I'm interested in. Then you're getting different KLT formulas. You can, yeah, you don't have to go to the momentum kernel thing. You can make it the original one that has the least number of terms and so on. Okay? And then the last application is, what if you apply to the case that one of the I left and I right is itself a particular? Okay? So what if you apply KLT relations to partial amplitudes? What do you get? Of course, you get the BCJ, not this BCJ relation, but the consequence of this, which is expansion of a partial amplitude into an n-3 factorial basis, right? So this is the last thing I want to say. So if your, say, your I left is a partial amplitude I call M pi, notice this pi, unlike this alpha and beta here, sorry, I'm summing over alpha and beta in some ordering basis, n-3 factorial basis. Here pi can be any ordering, okay? So for any pi, if you apply this formula, what you found is that you can expand them into a basis alpha with the transformation matrix is just M pi beta, M inverse beta alpha. Sorry, and you are summing over alpha beta of Sn-3. Okay, so this is the coefficient of your reducing any ordering to this. So everything is contained in your M matrix. So once you know this M alpha beta matrix, you can do the KLT and the reduction to a minimal basis for BCJ. So I guess I don't have time for the offshore thing. I'll do sorry, for the color kinematic thing. I'll do it in the next section. Okay, let me stop here. Thank you.
Questions?
Let's thank Sam.
Thank you.